I'm Ashley.
And I'm Lauren.
And this is our astronomy project about the life of a star. 10% of the observed mass in our galaxy is gas and dust. Stars form when this gas and dust reaches a cold temperature. A dense core at about 10K. That's 10K.
Kelvin.
Is the perfect setup for the birth of a star. This core is thousands of times larger than our solar system. As more and more mass comes together, it eventually collapses from the inside out, and the object at the center is called a protostar. This star is at the speedest stage of life. These protostars are actually larger than the main sequence stars when they release huge amounts of radiation and gas.
The star stops receiving more matter and is now a pre-main sequence star, or a young child. When the core temperature reaches 10 to the 7th Kelvin, hydrogen fusion begins, releasing tons of energy and stopping contraction. The last step of a pre-main sequence star is ditching the shell of gas and dust surrounding it. The star is now exposed to the universe and must begin its life as a grown-up, or a main sequence star. From this point on, stars take different routes depending on their mass. First, let's talk about the evolution of stars that have a mass of less than 8 times that of the Sun.
The smaller the star is, the longer it takes to form, and the longer it will live. Stars have a mass less than 0.4 solar masses are called red dwarfs, and they can remain on the main sequence for hundreds of billion years. To put that in perspective, our Sun is only going to live around 10 billion years. Red dwarfs have the lowest core temperature, the least amount of energy output, and they are the dimmest. They don't really do anything except slowly move down the main sequence. Only they have to cool down. These red dwarfs make up 85% of all the stars in our galaxy because they live for so long. At the very end of their lives, their core reaches about 10 million Kelvin, and core helium fusion begins, raising the temperature even more. After a dramatic inward helium flash, everything cools down and the star shrinks. It is now smaller, dimmer, and hotter than it was before. That is the life of a tiny star.
That's the life of a tiny star. There you go. But there are many stars that have mass bigger than 0.4 solar masses. These generate so much energy that the outer shell of gas expands and the internal temperature causes the entire star to grow giant size. Eventually, the surface will cool down and the giant will live its life as a cool, very luminous star. When these stars do start to reach the end of their life, it's because the core is finally running out of fuel. Cell fusion begins outside of the core, giving out heat and pressure and causing it to expand into a supergiant. The outer layers explode, losing 80% of the star's mass, and a planetary nebula is produced. The remaining core is called a white dwarf, and is roughly about the same size as Earth. So, down here, you can see a visual of what we just described. So stars that are less than 8 solar masses start off as a stellar nebula of gas and dust. And from there, goes on to the main sequence for however long, a few billion years, and then at the end of its life, turns into a red giant, and then explodes into a planetary nebula, and then the remaining core is a white dwarf, about the same size as planet Earth.
The end of a high-mass star's life begins the same way. It runs out of fuel. The iron in the core runs out of energy to use, and eventually too much pressure gets built up. Because of this, the star collapses on itself, and the outer layers bounce off from the core, sending out a shockwave. This is called a Type 2 supernova. This huge explosion is about 10 billion times as luminous as the Sun and produce every element on the periodic table. These supernovae remain brighter than entire galaxies for weeks until they eventually start to fade. The cool thing about supernovas is that with all the elements it produces, new stars and planets can be formed.
After a type 2 supernova, it can either head in two directions. If it's less than 3 solar masses, it becomes a neutron star, which is a dense star about the size of an Earth, tightly packed with, you guessed it, neutrons. If the core is larger than 3 solar masses, it collapses into a black hole. And we also illustrated this process. Stars bigger than 8 solar masses, which is really big. Starts off the same as a low mass star with the stellar nebula over here, and then it's a main sequence star, but it doesn't live as long as the small stars. Then it turns into a red supergiant, and then from there is the type 2 supernova we talked about, which can either proceed into a neutron star if it's smaller, or a black hole if it's bigger.
You don't want to get sucked into one of those.
No, you don't. And then, lastly, over here we have my cat and HR diagrams.
As you can see, this is a star at 0 years. These are the most massive, and these are the least massive. And then it goes all the way down 3 million years. As you can see here, all of the most massive stars have joined the main sequence. The least massive stars evolved the slowest and have not yet joined it. As time goes on, the top part of the main sequence empties out. The most massive stars have used up all of their energy and turned into red giants. Then, afterwards, 4 billion years, much of the main sequence is empty. Only the smallest stars remain on it, towards the bottom. Also, note that after a star passes through the red giant phase, it is taken off the diagram. Okay. So hopefully we made it clear that the life of a star really depends on how big it is in the first place. Stars are born due to a combination of materials floating in space and gravity. These stars will outlive us by billions and billions of years.
But that doesn't mean we should continue to study them! Woo!